So first I want to talk about, from a memory perspective, why are we having issues or trying to look at bringing in additional memory or additional memory architectures, and what is really happening in the memory landscape. Now this is not a new graph. You can see in the blue this is showing you the cost of DRAM. In the green it's showing you the cost of NAND. And you can see until about today that year on year respectively the cost was reducing 30 and 40%, and we were on a sort of this linear track of expectation. So the technology has been able to keep up, from device technology as well as patterning, to be able to do that. But today we're at about 20 nanometer node on memory technology, and as we go below that, we've got some additional challenges. We have, from a physical perspective and actually building the DRAM cell, from an equipment perspective and a manufacturing perspective. So there's a clear challenge from a memory point of view on being able to keep up with this tremendous amount of bandwidth that we're seeing. So I'm going to show you some chips that we actually build at eSilicon and the type of bandwidth that they're looking for and what it would take to meet that bandwidth, either using existing memory technologies and existing packaging versus going to some advanced technologies like high bandwidth memory and 2.5D type packaging. So we'll go through a little bit of each of those. So if you look at it from a market perspective, here we see that if you're looking at an enterprise networking solution, for example, you're at 300 gigabits per second bandwidth that you need, and these systems are ever increasing. There's just a tremendous amount of data that needs to be analyzed today. We're building chips that are greater than 3 terabits per second in data transfer rate right now. And if you look at a mobile phone, for instance, it's at 15 gigabits per second. Now if you look in the center here, the center chart, that's a 20-year-old chart showing you memory technologies from 95 until today. And if we were to look at trying to meet a terabit per second, let's say we're doing that with DDR3, it would require 40 external DDR3 chips to be able to meet a terabit per second. If we look at that from 40 nanometers, that goes down, DDR4, that goes down to 20, but still that's a lot. That's a lot of external memory to be able to manage when you're trying to hit a terabit per second. Now, our ASICs, many of them are greater than 1,500 pins. So you get into a pin limitation issue as well when you're trying to manage all of these data buses to this external memory. Now, from a power perspective, the power needs from a system level, they remain constant. So what happens is, as you add all of this external memory and you're having to route to all of this external memory, your system power becomes an issue and being able to manage the system level power. If you look at the chart on the left, you can see this just shows it's complements of SK Hynix, but it shows you the DDR3 going to GDDR5 and then going into HBM technology, and you can see this is showing you the milliwatts per gigabits per second per pin. So you can see that the advanced technologies, as you get into more of a stacking memory, are really beneficial. Now, what does this look like from a perspective of a packaged product? So if we're building ASICs, this is a large ASIC. It's now interacting with several external DRAMs. Think of these as DDR3 or DDR4. You can see that this is a fairly large system that you're having to manage. So, and really being able to meet the bandwidth, this is getting to be a very large and costly package. So on the right-hand side, this is showing you an ASIC. Now you have some high bandwidth memory stacks. These are on an interposer technology. So what is happening here is you're increasing your bandwidth. You're in a smaller footprint. You've got decreased power as well. So this looks like a pretty good solution. Now, what does this look like when you're actually trying to implement this type solution? Because many people are really frightened when you start talking about stacking and doing new packaging technologies. So this particular diagram on the upper left is showing you an HBM. This is a 4-high stack. And basically, each one of those lighter blue boxes is a DRAM, okay? And then these DRAMs are connected through silicon vias or TSVs. And there's a base die at the bottom. And that base die basically is what has the additional logic to be able to sort of manage these 8 different channels that you've put together. It manages the JTAG, the IEEE interfaces, the interface to the PHY, to the ASIC, etc. So this is kind of what that architecture looks like. Now, if you look at it on the right-hand side, this is what it would look like vertically if you were to slice it with the package. So you can see you've got the ASIC, and then you've got your 4-high stack. There's through silicon vias and micro bumps. Then what's below that is a silicon interposer. Now, there are different interposer types. There's organic, there's silicon, different technologies that are out there. In this particular case, we're showing silicon. And then, of course, that's communicating through bumps, and then, of course, to your organic laminate and your balls. So this is what the architecture looks like, okay? Now, if you think back 2 slides, okay, we were showing you an ASIC, and then we had all of those external memories in that package, or on that board. So that's really that first trend. So the first trend was, let's get the most we can out of the existing memory technology. Let's see how much we can get on a board, how many memories, how can we, sort of extend this life. Now we're seeing with customers that, they can't do that anymore. It just cannot meet the bandwidth requirements that they have. So we have customers now who are adopting 2.5D. They're going actually into production. And this is thought of as more of an expensive technology in that you have your extra steps for assembly, you have your extra costs for the interposer. But if you're building a very large, complex system, the percentage of that may not be so bad. If you're building a smaller, more consumer-type product that still may require a bandwidth, then this may be a costly solution. And so what we see happening in the third trend, and what will happen probably starting in 2018 and onward, is coming up with some new technologies for 2.5D. This is looking at organics. This is looking at build-ups. It's also looking at fan-out wafer-level packaging. So, but this kind of feeds the timeline. Right now, we're at this 2.5D adoption predominantly with silicon interposer today. So where does eSilicon fit in all of this? So eSilicon is an ASIC provider. We also develop our own IP. So in that, we're a semiconductor company. We do packaging and assembly tests, all of these things we control with our suppliers. And so about 5 years ago, we said, we do a lot of very high-level networking and communication chips, and we were seeing that we were going to run into this problem with bandwidth and with external memory. And we had to start looking at this from a packaging solution. So we started this program, and it's called Modular Z-Axis Integrated Circuit, or Mosaic, back in 2011. And we started taking a look at different interposer technologies. In fact, we started with organic technology and organic interposer. We started doing some daisy chain testing through the interposer and really understanding the routing and the signal integrity and power integrity issues, as well as just working with suppliers to make sure that we would have the right supply chain when customers came along. And in 2014, we had some limited projects that were actual customer projects that built on this. And now we've got 7 test chips. We have 2 customers going into production this year. And the next slide that I have will give you a little bit more detail about what those look like. But it really was a period of time of really developing and understanding this technology and making sure that a supply chain is in place, as well as developing the IP, because you have to have PHY IP that's going to be able to communicate with this HBM memory. So this is sort of our customer, our pictorial of the customer projects I was mentioning and the test chips. In the upper left, this is one of the first chips that we had done, and we actually did this with organic interposer. This was way back in the 2011, 2012 timeframe. The chip in the middle, this is 28 nanometer technology. This is one that we had done as a demonstration vehicle. In fact, someone on the floor probably has this in their booth and demonstrating this capability. And this is with Gen 1 HBM DRAM. The upper right, this is a product that will be going into production this year. It's using Gen 2 HBM. It has 4 stacks. That purple in the middle is just protecting our customers' proprietary information. But you can see there are 4 PHYs that are connected on chip to the HBM stacks external. And then on the bottom, these are 2 different customer programs also that we're working on at 14 nanometer. These are Gen 2, one of which will be going into production at the end of this year. And of course, all of these have varying different HBM stack configurations. So under the hood, what would this ASIC look like, right? So these are really large ASICs. They can have up to almost a terabit of embedded SRAM on board. That's a lot. Plus all of this memory that they're communicating with externally. This particular chip is 288 millimeters squared, so it's a big chip. It's in 14 nanometer technology. It has 60 lanes of multi-protocol SerDes. Now at eSilicon also, besides being an ASIC supplier, we also do IP development. One of the things that we find is that our customers require some sort of customization or differentiation in their chip. And so this has some customized memory, either to expand, the speed path to meet performance. And then there are areas in the chip where we've been able to use SRAM in an interesting architecture where we're able to decrease the density and decrease the performance as well. These are places that are not in high performance. eSilicon has been building CAMs, content addressable memories, for many, many generations. And so our TCAM is in this particular chip, and we have multiple different configurations to improve bandwidth and also just configurability in the way that the CAM would be used. Our PHY is on chip, as well as some special TIO that we build. And you can see this particular set of IP was built for Samsung technology, 14 LPP, and we'll be talking more about that in the Samsung booth. This is what the HBM5 looks like. This is showing you 8 channels. And really what we've done is anything that's in the critical path of meeting that 2 gigabit per second performance is done with handcrafted layout. Then, of course, the rest of the PHY is really meeting the JEDEC standards. So obviously it has the IEEE 1500, it has the micro bump repair, trimming, etc., all of the things that you would expect. This has been tested multiple times in silicon, and the way that we test it is we actually put it in a system with an HBM stack, and we actually test the PHY and its interaction through the interposer to the HBM stack. Other 2.5D services that eSilicon provides, we actually do the interposer design. So we do also the signal integrity and the power integrity. We have some very interesting pictures of some warpage analysis that we've done. And yeah, there's a lot that goes into really understanding the design of the interposer and really getting it right. Our PHY is designed really to be from about 4 millimeter communication between the ASIC and the memory stack. And then we are your source as far as bringing in the supply chain for the acquisition of the interposer, the packaging, the assembly, and then of course we're responsible for the yield as well. So we are a full service provider when it comes to 2.5D solutions. So that's the overview. We don't have a booth here today, but you're welcome to visit us at eSilicon.com, and love to hear from you. Thank you.